Yeah, okay. So you see, we live in a very unbalanced world, a world where the top 1% owns over half the world's wealth, a world where demand for resources far outweighs supply, and a world where I spend way longer debugging my code than actually writing it. So obviously these imbalances are really bad for us, but you know what they're even worse for? Machine learning classifiers. Specifically, unbalanced data poses a big problem in machine learning applications, and we're going to prove that to you.
All right, everybody, we're gonna get some real data right now in real time. So we're gonna run a quick poll. Turn your videos on and give me a thumbs up or thumbs down to this question. First, are you awake? I expect everyone's thumbs to be up. And keep them up, keep them up. And now for the next question. Ready? Are you pregnant? Anirudh, do I see your thumb up? No? Okay, good. Most likely, the distribution of yeses and nos looks like this chart right here. Far more no's than yes. It's very, very imbalanced. What happens if we use this data to train a pregnancy classifier? All it needs to be correct 97% of the time is to just say no, because 97% of the data is also no. But that doesn't mean it actually learns anything. Because of the data imbalance, it's likely that a model won't be able to actually distinguish between a pregnant person and a non-pregnant person. So it's confirmed, data imbalance is a serious problem in machine learning. This makes training large, unbalanced data sets hard, such as the dataset of the Earth. Because oceans cover 70% of the Earth, this data set will be heavily unbalanced towards oceans. And if we wanted to find the 0.001% of hurricanes in the data set, we need to train with really good balanced data. So how do we get balanced data from an unbalanced data set? Well, in our pregnancy example, we would want to pick and choose 50 pregnant examples and 50 non-pregnant examples to train. And there are many strategies to do this, such as oversampling, undersampling, or smoke.
But all of these strategies require that you have labeled data. And what if you don't even have labels to begin with? Then you wouldn't be able to pick and choose a balanced data set because you wouldn't know all of the labels. So then the only option for balancing unlabeled data is to simply get a bunch of it labeled. But this is expensive. We need to get a bunch of random data, label it, balance the data, and then discard the unnecessary labels. And this is also a huge waste of money and resources. But before we all go crying in despair, there actually is hope. What if we could balance data without depending on labels? What if you could deterministically choose which unlabeled data would be the best for labeling? And what if we could do all this automatically, thus saving both time and money? Well, instead of balancing a data set with labels, we'll show you how to do it with embeddings.
Yes. So we face the problem of balancing data without labels, and we claim that the solution is embeddings. But how do we do that? To reach our goal of creating the embeddings, to create the balanced data sets, remember that embeddings are just a numerical representation of our images. And like Mike presented earlier, similar images will have similar embeddings. And here we can look at the MNIST example again. During training, the images that are similar start forming better clusters with each other. So as you can see, all the ones started appearing together, all the twos started appearing, and so on. But also different digits are far from each other as well. 8s are far from 2s and 0s are far from 7s. This property of similar objects having similar embeddings is going to be crucial for balancing data sets in the future. So remember that our goal is to balance data using embeddings instead of labels. So how will this property help us out? Well, we claim that if we have an unbalanced data set, we can choose the most diverse embeddings, and as a result, we'll get a more balanced data set. But what exactly do we mean by the most diverse?
To help you understand this, we've created this hypothetical situation. Let's say the famous painter Bob Ross wants to create this bichromatic painting, and he wants to find the most diverse color palette with different shades of red and blue. So as you can see here, the x-axis is the intensity of the red, and the y-axis would be the intensity of the blue. We can think of each point as a different color, and so each color has an embedding, and we would want to pick the most diverse ones. First, our diversity algorithm starts by picking the black in the bottom left corner. Then the furthest away, or the most diverse point, is that fuchsia color in the top right. Then the most diverse color, furthest from both of them, is the top left color, the blue, and then it's the bottom right, then the center, and so on. I think you get the point. So since this algorithm is giving us the most distinct colors from this color palette, as you can see, it's essentially giving us the most diverse points. And that's pretty simple, it's pretty intuitive. So now we've helped Bob Ross with his artistic dilemma. But this isn't our primary focus. Our primary focus is balancing data in the real world using clustered embeddings. So how does this diversity algorithm apply to non-uniform and clustered data?
Well, let's take a look at how diversity runs on more clustered points, like these embeddings of satellite imagery. Each image that you see on the graph is the location of the embedding of that image on the UMAP plot. As you can see, images that look similar are clustered together, and images that are not as similar are farther apart. So for example, beaches are closer to beaches and harbors are closer to harbors. So when we run our diversity algorithm on these embeddings, it should choose an equal amount of images per class. Let's see it in action. First, the diversity algorithm chooses a forest image. Then the furthest from that one forest image would likely be a harbor image. That's what it chooses. Then the farthest from the harbor and the forest image would be the dense residential image at the top. Then the furthest from the three would be beaches at the bottom. And then it will go to the untouched cluster of airplanes and it will grab an airplane's image. So even though we do not know the labels of these images, this diversity algorithm can pick different things with almost equal probability because the embeddings are clustered. So by trying to choose one image per well-defined cluster at a time, this diversity algorithm will give us the best balanced data set we need.
But you see, up until now, we've been using embeddings that are well clustered. And so with all this theoretical stuff over, let's play with some real experiments where everything might not be just as perfect. Let's prove that we can use embeddings and our diversity algorithm to balance an unbalanced data set. So we'll be playing with circles today. We heard that circle classification is actually a really difficult machine learning problem. So we built this data set of 2D circles, and to make it a bit more fun and a bit more unbalanced, we made every other circle have 8 times as many points as the last. So in total, there are 4,500 points in this data set on this 2D axis. Our goal is to balance this data set using embeddings and a small 3-layer CNN with only a small fraction of the data labels to train. Here we have a random subset of the circles data set. Visually, it has a super large imbalance in it still, but here is another subset of the circles data set, which has been chosen by the diversity algorithm on the embeddings. Clearly, it's far more structured than the random set. But how do we know that it's actually more balanced than the one on the left? Well, we're going to use standard deviation as our metric for how imbalanced this thing is. If a data set has a large imbalance, then many of its class sizes would be far from the mean, and that would result in a large standard deviation. For a more balanced data set, the deviation from the mean will be far smaller, so that that data set would have a much smaller standard deviation. Overall, a lower standard deviation equates to a more balanced data set. And now we can go back to circles. And as you can see, the standard deviation for the diverse set is far smaller than the random, a drop from almost 80 to 29-ish. Thus, the diverse data set is far more balanced. Furthermore, if we use this diverse data for training, the accuracy of the classifier nearly doubles compared to random. And if we wanted to compare the accuracy of the diverse classifier using randomly selected data, we would need about 2.5 times more randomly selected data to match whatever we got from the diverse algorithm. So with only a fraction of the labels, we were able to get both a more balanced data set and a far better classifier using embeddings and our diversity algorithm. Isn't that cool?
Now for the last thing that we'll show you, we're going to cheaply balance this data set of unbalanced satellite imagery. Remember, traditionally, data scientists would randomly pick hundreds of images, get them labeled, and then balance from there. However, using embeddings, we can do the same thing starting with less than 100 labels. We will use, We will use a self-feeding approach to improve the dataset balance over multiple iterations. Here's the plan. Starting off with a tiny amount of labeled data, we will train a classifier, pass the dataset through it to get the embeddings, and find the most diverse embeddings, thus creating a bit more balanced training set. However, it won't be perfect right away, so we're going to repeat this process by training with our more balanced set and then picking the most diverse embeddings again. Then we'll add the newly selected diverse images to the training set and we'll repeat this process. Let's try it out. The first time, we pick a tiny random subset of labeled data, about 50 labeled images out of the 1800, and train a CNN, and then pass the entire data set through the same CNN to get the embeddings of each point. But remember, our data set is unbalanced, so we really only get a couple of actual good clusters in our data set, in our embeddings. But look at what the diversity algorithm shows. It's a more balanced data set, and you can see that by the decrease in standard deviation. Now let's look at the second iteration. When we train again and recreate the embeddings, we now see that there are more well-defined clusters. And what happens when we run diversity? We get a more balanced training data set because there are more clusters and our diversity algorithm is able to capitalize on that. This will be really good once we get into later iterations. So now we'll skip over to the 7th iteration to see something really interesting. We haven't circled it for you, but you can see that in the image here, the clusters are forming really well, even in the center of the really messy areas of the embeddings. And you can see that over all these iterations that the standard deviation of our data set has dropped as we've been selecting more balanced data. And as a result, now we'll look at the end results. You can see that overall, with our diversity algorithm, the standard deviation has dropped. And even though we've been also adding more images to our training data, our diversity algorithm is creating more balanced training data sets, so that also contributes to the validation accuracy improving. And now we have proven that just with a little bit of labeled data, we can get even better balanced data sets using embeddings instead of just relying on labels.
But here, everything that we've proved so far is contingent on the fact that we've had like a sufficient amount of labels. But you might be wondering, what if we had no labels at all? Then we would have nothing to train on, right? No, Suhas actually showed us that we can train without labels using SimCLR. So you can simply use the embeddings that we get from SimCLR to train to create a balanced data set as well. So without any labels, it actually is still possible to balance the data set using what we have done using embedding logic. Additionally, we can use SimCLR along with our embedding logic to balance the Earth dataset. Let's say we start with 500 million images in the dataset and our training limit is about 100,000 images. Then we can train SimCLR with a random set of data, generate the embeddings on this database, and then select diverse images to add to the training set. As we repeat this process, we can keep on training and picking the most diverse images. And after enough iterations, we eventually get a balanced data set of the Earth without using any labels at all, or barely using any, which is pretty amazing. As a result, we can see that we found a new method for balancing data sets. This method does not rely on blindly labeling data, and it doesn't involve shrinking our already thin wallets, and it does not rely entirely on labels, but it uses the power of embeddings and diversity. We began with the idea of balancing a data set until we found that using labels just wouldn't suffice. And now, after going through a rabbit hole of failures and findings, and unfortunately more failures, we found great value in using embeddings. So we created this scalable technique usable in any deep learning project that gives us balanced data, better classifiers, and more cost-efficient labels. And so when you have budget problems, who are you going to call?